Welcome to week 5. This is going to be a review for exam 1. I won't go through everything in this next part. I'll just talk through it. I did put down equations next to each of the subjects in here. So these are the topics we covered in weeks 1 through 4. We started with undamped free vibration. Topics we would make sure that you understand and you have equations for them on your equation sheet. Harmonic motion, velocity, and acceleration. So we have motion, velocity, and acceleration and harmonic, and just their relationships. Now the equation of motion, we want to be able to derive this for a mass spring system. Also do the equation of motion for a pendulum. You also do the equation of motion for a rigid body undamped system. Be able to do the FBD and the IBD of this in particular. I mean, you should be able to do the other two, the mass spring system and the pendulum, but also make sure you can do the rigid body. There could be varied different configurations on those. So we want to know the undamped natural frequency in a mass spring system. All right, so we could just, by which I mean, omega n is equal to the square root of k over m. You should really memorize that, by the way. An undamped period, which, we know that the natural frequency can also be found by taking omega n and dividing it by 2 pi. Remember that this is radians per second, so you need to divide by 2 pi radians per cycle in order to get the natural frequency into cycles per second, which is called a hertz. And remember that a period is 1 over that Fn. The general solution for this mass spring system, which is, we have mx double dot plus kx. So you could find the general solution, and that has coefficients in front of it, but we can also take initial conditions and find out a more general function. So we're going to have, we're taking x as a function of time and working through with that. Equivalent springs, if we add springs in series or parallel, we want to know how to do that. Different types of springs for deflection. Of course, you're making an equation sheet, so you don't need to necessarily put every variation that we have for that, but make sure that you can do that. Energy method, we're really not going to cover that on the exam because we didn't do it. I didn't have any practice problems that said stuff with that. Energy method, define effective mass. Again, not going to have that on the exam. And then also energy method, define the pendulum equation of motion. These are all things that were done, but not everything that was going to need to be for the exam. So we get rid of some of these things. They're about to get on top of the next column of things. So we have the equation of motion for a mass damper spring system when we have damped free vibrations, very similar to, the other one, but now we're going to have the mx double dot plus cx dot plus kx equals 0, right? And note that the general solution for this is something to the effect of, let's see if I can do this correctly, is going to be equal to some constant times e to the lambda 1t plus some constant times e to the lambda 2t. And so from the lambdas that we get from the characteristic equation, if we were to replace all the x's up above here with the form e to the lambda t, and then also x dot lambda e to the lambda t, and then x double dot, which is equal to lambda squared e to the lambda t. Replacing all the x's with that, we could find the characteristic equation, and so depending on what the lambdas are, we have these 3 different cases of critically damped, overdamped, and underdamped. Be able to do all of those things and be able to recognize them. Damping factor, which is taking the coefficient, the damping coefficient, and dividing it by the critical damping coefficient, which is 2m omega n. We could actually find that in other ways, but that's the easiest one, I think. The damped natural frequency, right? So that's going to be omega d. And we could also find FD if we wanted to, and then the damped period from that if we wanted to. The equations of motion in solution with initial conditions. Make sure that you know how to get it. I don't think I'd be testing on that, but that'd be a good thing to know. Make sure you have it written down and you can manipulate it. And you could also have the equation of motion for rigid body damped system. So with that, you'd actually need to use an FBD and an IBD in order to solve it. So make sure you can do that. Log decrement, natural log of xn over xn plus 1. So you take a look at the peak values, and you can also go like 1 over n if you have like XO over XN, let's call it right there, right? So this is the initial one right here, and this is any number after the initial one that you would have right under there, and you could find that on there. But anyway, the damping factor from long decrement, I'm not going to write down the equation because I don't have it in front of me, but make sure that you can get that. Coulomb damping we're not going to cover, and finding the coefficient of friction from Coulomb damping system response we're not going to cover that. I don't think I even did this example in class, so I just wanted you to know about the Coulomb damping and not actually so let's see, how far did we get into this? Do I want to do an example? I guess I'll do the examples separately, so we'll be right back. And I got to go to here to stop the video right here. Yeah, 7 minutes is enough.